Okay, welcome to all my audience today for speaking about Tecplot Chorus. And today we have a special guest, and we will see an example from aerospace optimization additionally. My name is Jens Warkal. I'm a physicist working with Genius Graphics, and the agenda for today is short our contact data, because it's important that you have always a chance to contact us. Some words about our company, but not too much. A little live demonstration, Tecplot Chorus in a nutshell. It's maybe 3 minutes or something, so that you have a basic understanding what Tecplot Chorus means. And then we are going to the main part, to Chorus for aerospace optimization, where I have today the guest speaker, Mr. Ronsheimer from the DLR in Germany. And so we have a look at Chorus for aerospace optimization. So our contact data, my contact data, Jens Warkal from Genius Graphics, is jens.warkal@geniusgraphics.de. You will find us in the internet. You can call me directly. It always saves time to call me. Or if you have any questions to our guest speaker later, please note now arno.ronsheimer@dlr.de. I will show this later again. So okay. Of course, by the way, we have later time for question and answers, so please wait for this if you have questions. Just some words about us. Genius Graphics is, you can call it Tecplot Europe. We are here in Germany, near to Regensburg, and what we are doing is we are responsible for European sales in Tecplot, all products, and we are doing training, measurements, consulting, and implementation. So if you have any questions, please always contact us directly. Let's speak about Tecplot Chorus in a nutshell. So I don't know how it is with you, but many of our customers, they find that the data is spread out over hundreds or sometimes thousands of files, directories, subdirectories, servers, networks, and who knows what all, and it becomes impossible to maintain even a minimal overview. So we will see today how to keep always the overview over your data, and in addition to this, Tecplot Chorus will help you to simplify and shorten your design process. What we will see, we will have a look at a case later where potentially critical information is lost, and we will understand how Tecplot Chorus can avoid this. And it will be demonstrated how working with Tecplot Chorus saves tremendous amounts of time. Well, that's it in short. So these are just words about Tecplot Chorus. So let's see Tecplot Chorus in action. First, let's have a look at a data structure. So what we have here are, in this very tiny case, we have 32 directories and 32 simulations which are sorted by 3 parameters. So we have here the Mach number, and then we have some 2 angles, which is alpha and beta. So we have 3 parameters. So this is sorted after parameters, and every information can be hidden in this directory. So it can be simulation files from 3D, from 2D simulations files, combined simulations. Then we can have history data. We can have, for example, convergence tables or whatever. And the idea is to collect all of this information and to make it available for you. So in our simple example, we loaded just all the information into a table, and this table is displayed then in Tecplot Chorus. So if I open the product and we have a look at this UAV test session, then we see in the very top a table which contains the parameters. In this case, 3 independent parameters, Mach, alpha, beta. Then we have dependent integrated forces, which are available here. And the first you can do is, for example, sort after parameters. Then you can access the information directly, meaning that, for example, if you are interested now in the result files of the first, let's say, 3 three rows here, the three first simulation files, then you simply have a look at the images and you directly can compare the results files here. That's one of the ways you work with it, or show the labels. And if you have more results as plots, then simply feel free to display all of them and to have an overview what happened in this simulation. You have in this table direct access to your data, so you can view images, you can view the data itself, you can open directly the data sets, so you are never lost and with all your spread data sets. You can create images, which is automatically done. So these images are available later, and you manage them and understand so deeply what happened. You can create data. What does it mean? Let's say that you have huge simulation files. Then you will extract information like slices, like isosurfaces, like streamlines, and you have reduced data available. And this is absolutely handy if you have huge data sets. Yeah, that's it. You can extract variables. This is just one point, that you can combine parameters and so on. Or you can have own actions, which means that, for example, you can call external programs like mathematical tools to do things like complex statistics. The next point is that you will be interested perhaps in your trends. What happens in your data sets, for example, what would have happened if I would have done simulations between those simulations which I did, because we see here is a table which displays the results of all the simulations. This table is a matrix sorted by Mach and Alpha, and here you see a so-called surrogate model which shows us what would happen between those simulations. So every of these nodes here, you have to imagine every of these nodes here is one simulation, and so you have from everywhere you can see your data, you can access your data. So I could open now the data sets and so on. On the right side we see some line plots which are showing Mach and drag, and we see here as a dotted line, we see here the surrogate model for this, so we can approximate directly the values which would be available here. The important point is you have additionally filters. This means that you can focus always your view on exactly what you want to see, so you can filter after all the parameters, and you say and you see then that it's this is available here, and now we see only that information which we would like to see. Okay, this was a very tiny introduction into Tecplot Chorus, and of course we will see it in detail if we are speaking about the real case. So let me close now Tecplot Chorus, and let me go back to my presentation. So here we are, and now we are speaking about a case study, the DLR and aerospace optimization, with our guest speaker Arno Ronsheimer. And this is a moment where I would say I switch the screen to you. Arno, can you hear me?
Yes, hello everybody.
Okay, great. So let me switch the screen to your screen, and I make you the presenter now.
Yes. Okay, I will start with a short introduction. Everyone can see my screen, yes?
Can you speak a little bit louder?
Yes.
I can see your screen, Arno. Everything is fine. You can start.
Yes, okay, I start with a short introduction of my problem. This is about tail drag optimization for generic transport aircraft configuration. And okay, this is about the motivation to doing this study here. The problem is that after loading transport aircraft suffers from fuselage upsweep drag, and here the fluid curls up in so-called tail vortices and escapes from the aircraft, and there is less fluid available for a pressure recovery, and this means more drag and less lift. To reduce its upsweep drag, tail strakes are used. These tail strakes produce counter-rotating vortices to weaken the tail vortices. The problem is where is the optimal tail strake position, and here design optimization helps. To apply now design optimization, the first thing is the parameterization of the tail strake problem, and here CATIA version 5 is used. CATIA generates a measurable geometry for given design parameters, and these design parameters are at the cross point of an ISO line in U direction and also an ISO curve in V direction. And there's an additional design parameter which defines tangent of the tail strake according to the U direction. And these, for the optimization, these parameters are now limited to not hit maybe the intersection with the symmetry plane, or maybe intersect with the closing panel of the fuselage. So this is now design optimization loop. On top we have an optimizer. It's here the suplex method is used. The suplex method sends design parameters to the geometry modeling, which is here done with CATIA version 5. It takes about 20 seconds, and then geometry, measurable geometry, is given to the grid generation program, which is from Centaursoft, using a hybrid prismatic and tetrahedral grids. It takes about 5 minutes to measure geometry. And then finally the DLR flow solver tau is used to solve the problem. And here 2 adaptations has been applied. Then finally the lift and drag ratio, which is evaluated from the flow field, is given back to the optimizer, and optimizer decides about new design parameters for the next cycle. And here we see now the history of all these cycles. Each single point is geometry plus a grid generation plus a CFD calculation, and it takes about 10 hours turnaround time. Now here we have an ideal asymptotic convergence of the objective, and we can see that there's an improvement of about 14% from the first from starting configuration to the optimized configuration, which is here number 44. And we have a 28% difference between the worst, this was number 4, and 44 strake position. And to observe the optimization progress is very important here. This plot tells you if the optimization is working, and in this case it does it well. The problem here, however, is that from cycle to cycle, about 1 day is required for the CFD solution. We have a cluster here with the queuing system, and each CFD calculation is queued, and you have to wait for a free processor. Sometimes I start an optimization and I go on holidays, and when I come back I analyze the results. And at this point, using Tecplot Chorus would be very helpful, because then each dot of the history plot is linked to a corresponding CFD solution. Therefore, it is very easy to open the corresponding CFD results for deeper analysis with Tecplot Chorus directly from this history plot. And the sorting function in Chorus helps you to find the minimum and maximum values immediately. And here I used this study has been performed 2 years ago. Here I used the Tecplot probing function to find this. And also there's a sorting function in Chorus that helps you to find minimum and maximum values immediately. I think we'll see much more useful features, of course, in the following live demonstration. And now here are the surface plots. Once the optimization is finished and several checks are compared, interest is focused on the best and worst candidates. So here I prepared a layout showing the configuration from a back view position and plotted the surface streamlines. And this layout will be used later in the Chorus demo to produce several such plots in a very easy way. Again, to the plot here a fluid cutoff is used to visualize pressure coefficients greater than 0. This is done with Tecplot, and the information is now very simple. More green tells me more lift and less drag. And now let me proceed with the 3-dimensional results. So it is easy to see here that in the worst case here, the strake amplifies the vortices, while in the optimized case, the tail strake truncates the tail vortices. And in this case, the analysis of the volume data helps me to understand the effects better. And these volume files are very big, and therefore, during the optimization runs, I deleted the volume results. One reason doing that was disk space. Another one was the manual effort and the time required to post-process the volume results. And afterwards, I recomputed number 4 and number 44 and analyzed it here. And I only keep the surface results in each cycle. Maybe I have thrown some interesting and useful intermediate results away.
For sure.
Yes. And these volume stream plots would be very useful to have in order to understand the phenomena. Volume data processing with standard Tecplot is daily routine for me and many of my colleagues, but still requires manual effort and time. But I'm very confident that I will save in time and manual effort with Tecplot Chorus processing all the volume data later. There are finally some closing remarks about optimization. It is still an exciting business. Often no one can tell you that your problem has an optimal solution at all. The optimal may be outside the parameter ranges. The CFD solution is not accurate enough, and the cost function becomes noisy due to numerical errors, and the optimization algorithm which you have chosen cannot tackle this. Normally, if I'm not on holiday, it is useful to observe the optimization when it runs and inspects the history and watch the design variables and the surface data. Yes, this can be easily done in Chorus, and I can use it as a management tool for my data.
Okay. Yeah, Arno, thank you very much for the presentation so far. Thank you. One further remark about your volume solutions which you needed to delete. Of course, for future projects, you can extract slices, ISO surfaces and streamlines of your volume data and then delete the volume files. So now you still have the important data available in Chorus. So, okay. Just one remark. Okay, but let us go now directly to the Chorus. Let us see now Chorus in action. And we have a look at your case where we both worked together on. And I will switch now back on my screen, okay?
Okay.
So let me do that. Let me switch to my screen. Just 1 second. Make presenter. So, show my screen, that's fine for me. And if you would like to have control over my computer because you want to show something, I give you additionally my mouse and keyboard, okay?
Okay, yes.
So, it should work. Can you test it? Does it work? Yes, it works fine.
Yes.
Thank you very
Okay.
much. Okay, let me go to Chorus and now I directly open Chorus with our project and here we are. Here we see results and on the left is the convergence of every CFD calculation. On the right we see the surface plots, Arno.
Yes, it really impressed me to see an animation of all the results here. First, can you scroll through the results and show me the animation?
Yeah, for sure, I do that. Just a second. So here we go now through the results. And can you speak a little bit more about what you or how this would help you?
Yes, the animation shows me how the optimizer has worked, and it worked as it expected. At the beginning, large changes of design variables occurred, and later the change becomes smaller and smaller. And finally we see more green here.
Yeah, that's true.
Now it would be interesting to show the table view.
Okay, yeah. Let me go away from this view and let me open the table view here, Arno. Arno, you told me this view is interesting because it is easy to sort by the parameters. It is especially easy to access the data sets by just clicking, right? Yeah?
Yes, exactly. In standard post-processing, you have to search the correct data set. You need to jump through many directories, and this costs time. In Chorus, you can open them directly.
That's true, yes. Exactly, Arno. Okay, and yeah, here we have the data completely linked. So I will tell the audience a little bit about this view. I told you before, so what you can do now with all this with all the simulations here, for example, simulations, of course, can be experimental data, combined data, and so on. You can, for example, view the images which you created with styles. You can view the data, you can create images, yeah, with your different styles, and you can create data, that's what I talked before, so you can extract important information like surfaces and so on, and extracting various. Arno, should I open some data sets?
Yes, Jens, please open the first data sets in Tecplot.
Okay.
Okay. So in
just 1 second, I can't. Let me just repeat that. I'm not sure what happened. I guess I did something wrong. Oh, monitor data. I'm sorry about it. I used the monitor data which is available too. So that once again, in Chorus you have access to all your data, whatever it is, history data, monitor data, and so on. And of course, I need to show the surface data here. So let's do that. It just takes a second. Okay.
Yeah. Okay. Yeah, in many cases, optimization did not run in such a perfect manner as I showed. And first of all, it is important to check if the parameterization works properly. And normally in the first iteration, the optimization algorithm varies the design parameters one after another. And yeah, please, could you show me additionally the parameters, I cycle, U, V, and V?
Yeah. Just 1 second. U, V, and V. Here we are. I can rearrange it if you like to. So
oh, no, that's okay.
Just 1 second, I rearrange it for you so it's better to see. Okay. Yeah, that's it. And what would you typically understand by turning on these parameters?
Yes, I can see that the parameterization works. This means that each time the cycle starts, new design parameters which came from the optimizer have been passed to the CAD system correctly. The meshing software has meshed the geometry, and the CFD solver has converged and has produced new results. And one has to consider that all software in the optimization loop runs automatically in batch mode and also on different platforms here.
Okay, I understand. So, okay, great. What is the next step, Arno?
Yes, okay, please close Tecplot and show the first 4 data sets with the mesh style.
Yeah. Okay.
I would like to see if the adaptation has worked correctly. Yeah.
So here we are, and I rearrange the frames. Okay.
No, I like it how easy it is. Fast, you can open more than 1 data set with styles and Chorus. They're automatically arranged in frames and linked here.
Yeah.
That saves time and work.
Okay.
What I can see here is that the adaptation parameters have been set correctly, and the trace of the vortex should be visible on the surface width, and it does, yes. So in the vortex, higher gradients occur, and therefore the adaptation inserts mesh points here. And as I see, the adaptation has worked as I expected it.
Oh, that's great. Okay. Arno, what's the next step? So what can I do next?
Yeah, can you please show me the history data in Chorus as XY plot?
Okay, fine. So let's have a look at the history plot, which is visible now here. Okay. So this is your history plot, which we saw before in your presentation, right? It's the same one. And
Yes.
please tell us, the audience and me, something about it.
But can you switch the design here of objective?
Thank you very much. Of course, this is wrong, so I have to switch to L over D, right?
Because the optimizer always searches for minimum, so I have to switch the sign of L over D, and we searched for a maximum.
Okay.
Okay. So, yes. Okay.
So you see the minimum here.
Yeah, the minimum, but what we are searching for is a maximum. Yeah, can you go now back to the table view and to find out where is the minimum and maximum?
Yeah, that's very easy to do because we
the minimum was easy, but the maximum was a problem. That's
true. Yes, it might be here, over there, something.
Yes,
so
so
if I resort it, now you have the maximum in the top and the minimum.
Yes, okay, we see it. Yes, we see immediately this is 44 here, and the minimum, where that was easy. It should be the number 4. Yes, okay.
Yeah, this is a really.
Really working with table view is very handy in Chorus here.
Yeah. Okay.
Yeah, the problem is now I don't know if the optimal configuration is inside the parameter ranges. Inside the prescribed ranges I showed in my presentation. And now some scatter plots with the design variables V, U, and V would be very useful again.
Okay, great, for sure. Just let me create them for you, Arno.
Yeah.
First, it's I cycle and phi. Second is I cycle and U. Next is, it just takes a minute to do that, and this is
maybe L over D, yes.
And phi. Okay.
Oh yes. And now can you color that after L over D?
Yeah. Okay, just wait. It's better, right, to have that colored in different way. L over D and L over D. Okay, the color has been changed.
Thank you. Yes, it's now easy to see that the optimal configuration is between maximum and minimum, and therefore the optimum is inside the prescribed ranges, so we can be sure that this is true maximum with 0 gradients.
Okay, great, I understand. And just to add that, we can easily filter these points by phi, U, and V. So we saw in the short presentation that we have this filtering, and so feel free to use it here. But you know that very well, and I guess that you use it so oftenly. So.
Yeah, but a great feature. It's very easy, and because one can focus on specific value ranges and see the filtering, all the views here. This is very nice.
Exactly.
Now please let me mark single values of some candidates which came close to the parameter ranges. I will show you which points have to be selected.
Okay, okay. You have mouse control, right? Might you show that again on the left side? Yeah. Okay, that one.
This one.
This one.
This one here.
And
maybe here. This one.
Okay, okay. I will select them and.
Yes.
Just a second. One. One.
Okay.
2, 3. And view the images. Once again, I did miss one of these points, unfortunately, but let me try it again.
But I think this is not so important, this point.
Okay, okay, then it's fine. So, here we are. Here we have these 3 images. And let me go to surface data, perhaps make it bigger and display labels. So,
yes, these pictures show me how close the optimizer has come to the parameter ranges. It's still impressive how easy it is to access these pictures here.
Yeah.
Yeah. It's corresponding to the points here. Yeah. Now please show me the other way to see the pictures sorted by the parameters, like the position U. It's also very interesting.
Okay, this is what you're talking about. Of course, this is the matrix view. So let me load this. The matrix view. Here we are. And now tag and U and show the surface data. So yeah, would you please say some more words why this is useful for you?
Can you scroll through it?
Yep.
So we can see how the streak is moving. Yes, from the middle to the end and fuselage, and yes, and we can see how the area of positive pressure is changing.
Okay, that's great. So let me try something different out, and let me go to a UV matrix. Just a second. Oh, wow, that's pretty empty.
Yes, we can see many caps here, but this is clear. We used deterministic optimizer. If we had used the design of experiment method, we would see the completely filled matrix, I think.
Okay, I understand. Yeah.
Finally, I would like to see what are the difference between the starting point, the worst case was number 4, and the best case, 44. Can you open them now for a deeper analysis in Tecplot?
Okay, that's easy. So just resort and open, or we know meanwhile the numbers 1, 4, 44, and have a look at the data. Okay, done.
Okay, nice.
There you go.
Please show me more streamlines on the fuselage and strakes here.
I'm placing much more streamlines now. Here we are. And streamlines on the I will uncouple the third one.
Also on the bottom of the strake?
Yeah. I will do that, but I just want to uncouple the third frame. Chorus automatically couples, and it's better to have this one uncoupled. So frame linking and uncouple. That means I can go down here now and rotate a little bit, and it's it's easier to place screen traces there. Okay, let me place screen traces in a second. Screen traces, and yeah, here we are, screen traces, and once again, and yeah, what do you see here now?
I can see something special happens here on the lower side of the optimized track. We can see that the streamlines are going smooth. In the mainstream direction, it would now be useful to have all volume solutions available to analyze this in detail, but unfortunately only some are available. And but with Tecplot Chorus, I would have generated the plots for all volume solutions, and yes, I have used it for deeper analysis.
Yeah. That's it, exactly. So, okay, thank you. Thank you. Finally, Arno, after this work, how would you say Tecplot Chorus will help you in the future projects?
Yeah, I'm doing post-processing of data with Tecplot for more than 20 years now, and today analyze of three-dimensional volume data is a daily routine, but I'm still doing it manually and only for a few number of selected data sets. But now I see a way to work very easily with numerous data sets, finding out specific characteristics without wasting my time or probably missing important information. And I'm looking forward to using Tecplot Chorus in my next project.
Great. Okay. Yeah. Thank you very much, Arno. And yeah.
I would like to thank the audience for the interest, and I would like to thank you, Jens, for the assistance in this webinar. Thank you.
Yeah, you are welcome. You are welcome. Okay, that's it. So I would say I come back to my my PowerPoint presentation, but just to show you my and of course Arno's contact data. So here we are. This is our contact data. Arno Ronsheimer from the DLR and Arno.Ronsheimer at dlr.de. Me is jens.waker@geniusgraphics.de. You see my telephone number, you will find us in the internet, so if you lost that, no problem at all. And I would say now we are ready for question and answers, and please feel free to place your, to chat your questions now. We have, what do I see? We have at least 8-9 minutes time to answer your question, and no problem to stay a bit longer. So you should see the chat window below in your GoToWebinar window, and feel free to place your question. It can be a question to me about Chorus, and of course to Arno about his optimization, or about other projects. So feel free to ask questions. If you have any problems, you can raise your hand, by the way. I see there is a hand raised from Ashka Gorbani. Okay. So I have a look now at the question window. Oh, we are getting some questions. I have to sort them first. So let me begin from the very beginning, and hopefully I can answer any of your questions today. Otherwise, of course, we will contact you. These questions are saved and we can contact you without problems. Could you show me the data structure required by Tecplot Chorus? Folder structure with style files. Yeah, of course, this is possible. The data structure normally used by Tecplot Chorus is that you place your data sets in one specific, the easiest way, by the way, is that you place your data in a directory, which in this case is, you can see it here, and then if you create a style sheet, then this will be done usually in Tecplot Chorus. I can show you an example how easy that works. So let's say that you want to see now this data point here, and now I would like to view the data, and Tecplot opens, I see the data set, and now I would like to have another style. So if we do some action here, and I, for example, change the contour variable, which might be absolutely not useful, so please, Arno, forgive me if we see some nonsense. So here we are now, we have a different style, and I rotated a little bit around or something, so let me do that. If we have now a new style, then simply go to Chorus, the Chorus add-on which you see here, save as a template, call it whatever, and save it. That's it. Now it's available. You can go back to Tecplot Chorus and easily access data. So if you want to compare now this point and this point, then it's easy, just mark these points, these simulations. You have access now to your data, and you can easily go here to view data and, for example, use the whatever style, and after a second Tecplot will open and you will see both results. So here we are, and now you can compare easily both different designs here, what happened here, and so on. So hopefully this answers your question. Of course, feel free to contact me, or we can, there's a remark.
Jens, I have a comment. This is Harsh here. The question may also have been the data structure required to load the data into Chorus. If you could quickly show the CSV table.
Okay.
That would also be helpful.
Okay, Martin, if you mean the easiest way to get in your data into Tecplot, because we saw this table in Chorus, we saw this table here, which contains all the parameters, and if you click here, you can say view data, and then you have a choice between different data sets. How does it come? Where does it come from? So one word about that, it's a simple table. So if we are going here to the basic directory, output 2 is the name of the file. Let me open it, for example, in Vim or whatever, in Excel. Then you see that we have in the top here, we have simply names for your data sets. And here we see links to your data sets, and after this data sets, or wherever they are, there you will find your parameters. Here the independent parameters, Mach, Alpha, and Beta, and then drag, lift, and so on as integrated forces. So you combine the links to your data, and you combine this with a complete parameter space, and then you simply load it into Tecplot Chorus, and then you have it available exactly in the way which you saw here. So then you have this table available, and you have the link to your data. Thank you very much for commenting this, Harsh. Let me go. Very important question, because we have now a question here, at least one question to Arno. Did you read the question from Carlos Souza?
Yes, I read it. It's I would say it's Mach number 0.68. This is a typical cruise Mach number for this type of configurations. That's cruise flight condition.
Okay. Is it I'm not the expert, so you see me. Okay, fine. The next question here, one question is how you load the data and assign the parameters to your simulation results data. I guess this question may be answered. So it is easy to load such a table, and there you have all the parameters in. But by the way, you can. It is important to understand that you can create afterwards. You can, for example, integrate in Tecplot, in Tecplot 360, and give those integration results back to Tecplot Chorus, by the way. So it's not always the case that you have a completely filled table. Usually you have at least the independent parameters. For example, here in this case what we see is phi, u, and v, for example, but this is something different because it's another type of optimization. You have independent parameters, and dependent parameters can be calculated afterwards. So, okay. Here's one question about the organization, the organized data, like interpolated or surface data or historical data. How does it work to load this data? So what we usually do is something very, very simple. I usually create a very tiny Python script which runs through the directories, and then it selects or collects the parameters which are needed, like from history files. They are placed in such a table, and then this table is easily loaded. So I have some modules doing this work which are parsing for strings and so on. That's easy to do, and of course we will assist you if there are any questions how to do that. We have some files helping you, and that's it. Okay, we are over time now, but I will have a look at exactly your question. Okay, one question is answered. Another, thank you. How do I interface Python scripts in Chorus? You have, for example, the question is a little bit tricky, because first, of course, you have Python available in Tecplot. This means that if I view, for example, data, yeah, I have always the option to run a macro, and this can mean that this macro once again opens a Python script which is doing something. Another point is that you can directly couple Tecplot Chorus with Python, because these actions which you see here, like call Skylab or something, yeah, open data externally, these are actions which are simply links to Python scripts which are doing something for you. Yeah, that's another point where Chorus and Python is linked. Okay, yeah, it seems to answer your question definitely. So, once again, we are over time now, but nevertheless, I don't want to block you if you have a further question. I have that time today for further minutes if there is any question. Otherwise, I would say that's it for today. So if you have any questions to me or to Arno about optimization, he's the expert, and questions about Tecplot Chorus, please ask me. There are 13, well, we have so far 15 participants available still, so if there's any further question, please let me know. Okay, I don't see further questions. Arno, I would say, yeah, that's it for today. So once again, thank you all for participating in my online webinar, and we will contact you. About this session, and well, that's it. Have a nice day. Goodbye. Goodbye, Arno.
Goodbye.